Okay, welcome you all to the basic level CFD workshop in OpenFOAM. So this tutorial is aimed to be a beginner's level training session, and this tutorial will be demonstrated in the foundation version of OpenFOAM, that is the ORG version, and the version we will be using is version 9. So, please feel free to post your queries in the chat. So the basic outline of this session is that we will be simulating 2D laminar flow in a channel, and then we'll also be simulating the 2D turbulent flow in a channel. So the problem definition is to set up a case for laminar flow through a channel, and after that we will be looking at how to set up a case for turbulent flow through a channel using K-epsilon model, and we will also post-process some of the results in ParaView if time permits. So this is the basic case structure of our case, which was also previously explained by other my colleagues. So I won't be diving deep into this case structure or the folder structure. So the zero contains the boundary conditions, the initial and the boundary conditions. The constant contains the like the physical properties, transfer properties, and turbulent properties files. And the system will contain the control dict, block mesh dict, FV schemes, and these FV solutions. These are the settings, like the we assign the settings of our simulation in the system folder. The layout or the files are similar to the previous cases that have been demonstrated. Okay, so first we will be simulating a 2D laminar flow in a channel. So this is our channel that is shown in the figure. So we have the inlet, outlet, upper one and lower wall as boundaries, and front and back as empty, because we are doing the 2D simulation. And the Reynolds number that we have chosen for our laminar flow is 500. So our average velocity at the inlet is 0.005 meter per second. So if you input these values in the Reynolds number formula, then you get the Reynolds number as 500. So basically, this is the kinematic viscosity, which is the value of 1 minus 5 meter square per second. So before running our case, I'll let you know where these cases are available and where you can download it from. So if you go to the FOSSEE website at cfd.fossee.in, so you can see that there are spoken tutorials available in this website. So if you go to the spoken tutorials, so you can see that you can access the OpenFOAM spoken tutorials from the CFD website as well. So first of all, there are many tutorials. So for the beginners, it is very this site is very good reference to start with. So they have started they demonstrated for the how to set up the simple cases. So this case is also a simple case for the 2D channel geometry and mesh. So you can see in this, if you go inside to this, then you can see that there is a video available to how to create a 2D channel geometry and mesh. So you can go to this video. And the other good thing about this site is that there are also the code files available. So you can download the code files as well from these. You can see in the right hand side, you can see there are the code files, and there are slides, and also we have the additional reading materials for each and every cases which needs another reference for the cases to understand the theoretical part. So there is an additional reading material as well. So first of all, I will not dive deep into how to create a simple mesh. So you can check these videos, and there is also another video on how to simulate a 2D turbulent flow in a channel using OpenFOAM. So there are basically two uh, links. So this one is one, and the other turbulence modeling in OpenFOAM. This is the other link. So the video is very detailed, and the more detailed is the additional reading material. So you can access this additional reading material from these sites as well. Okay. So now let's look at our case setup. So first of all, let's see look at the laminar flow for the Reynolds number 500 case. So I have already run the case in my system. So let's first look at. I want to explain the the control dict FV schemes and FV solution, because this has been already been explained by in the previous demonstrations. So I'll give a brief overview in the block mesh. So block mesh, we have a structured hexaedral uniform meshing. So simple grading we have applied, and we have a 75 number of cells in the X, 30 in Y, and one in the Z direction. The one in the Z direction due to the 2D due to our 2D simulation, because we are running a 2D simulation, so we don't want any more number of cells in the Z direction. And also for a 2D simulation, we need to keep the front and back as empty. So this is our block mesh, which will create the generate our mesh. So after that, in the control dict, you can see that which solvers we have used. So we have used the simple boom solver, which is a steady state incompressible flow solver for laminar as well as turbulent flow. So we have run for the so in the simple form, this time is not important. This just refers to at the pseudo time. So because in simple form it is a steady state solver, so actually there is no importance of time step here. Okay, so I have already run the laminar case. So let's look at the boundary condition now. So as I have already shown in my slide, that the Reynolds number is 500. So we have velocity average at 0.005, which I have used here. And for the pressure, the boundary conditions are like the general gradient, fixed value. So you can always refer to what this means after this demonstration also. And the other important thing is that these transport properties and the turbulence properties. So if you see these transport and turbulence properties, so in the turbulence properties, you define which turbulent model to use. So in our case, we are using the first case, we are using the laminar turbulence model, and the transport properties is where you set your physical properties of the flow, that is like the kinematic viscosity, that is new. So we have used 1e minus 0.05, which was also in the slide shown. So these are the basic files to set up our case and the basic inputs that we need to put in our files to run our case. So after these are set up, then we have a separate script called the all run script. So in the all run script, you type all the commands that you need to run to run your case or to run the simulation. So first we will be running the block mesh, which will generate our mesh, and after that we need to run our solver, which is simple form. So if you use the parallel processing, then you can also there will be additional commands like the decompose par and MPI run commands. So in our case, I have just used the serial processing, so there is no such parallel processing commands in my all run files. So this will be executed one after another automatically. So we don't need to type each and every command in our terminal. So this script will automatically run the. So let me see on my file. So I've already run the case. So I will not be running the case again due to the time constraint, and this will require more time to run. So in order to run the all run script, you just need to type // and all run. So if you after you type this command and then hit enter, then the commands in the all run script will be executed automatically. So you just need to type this and hit and press enter. So right now my cases are run. So let me, before post processing, let me show you how to set up a case for turbulent flow also as well. So before we set up the case for the turbulent flow, you need to have a good idea on what the turbulence, how to model the turbulence, or what parameters are required to model the turbulent flow. So there is a very good reading material as I've already shown you. So you please go through this reading material before you. This is a very good starting point if you are new to the turbulence modeling. They have a very detailed calculation and detailed explanation of how we need to model the turbulent flow parameters like the y plus values, and for what value of y plus we need to assign the gradings. So like because in the turbulent flow, y plus is very important. So near the walls, if you are resolving the viscous soft layer, then the y plus should be very less than 1. Similarly, if you are going over y plus of 100, then we need to use the log layer approximation. That is, when we go to the log layer region, that you need to use wall functions and all these things. You can refer to this document. There is a very detailed explanation, and all these values, how do you calculate these values, the numerical values are also calculated and shown here. So I have also used these value in my in values in my cases. So if you look at the turbulent case, so let's see at the turbulent case using k epsilon model. Okay, using k epsilon model. So this is the case. So if you look at the boundary conditions for all the k epsilon, so k is the turbulent kinetic energy, epsilon is the dissipation rate, and nu t is the eddy viscosity. So p and u are the boundary conditions for pressure and velocity. So if you see that inside the epsilon file, so you can see that I have assigned this value of 0.61. But if you want to know how to calculate this value, then you can refer to this document. So you can see that how the calculations are made as shown here. Similarly, for omega, for k, all the calculations are shown here. So I won't dive deeper into these calculations. And these are the boundary conditions. So we have for the inlet, we have used the assign the internal field of 0.61 as well. So for the outlet, zero gradient for also, and we have used, and the most important thing to notice is we are using k epsilon model, that is the high Reynolds number formulation. So k epsilon model, we need to, if you use k epsilon model and the y plus is greater than 30, then we should use the wall function to model the logarithmic change of velocity with the height from the wall. So the wall function will accommodate because when y plus is very greater or greater than 30, then we cannot resolve the viscous soft layer properly. So if when we cannot resolve that viscous soft layer, then we need to use wall functions, so that these wall functions will automatically accommodate for that viscous soft layer which we have not resolved. So you can look or you can see how the wall functions works for different. So basically, wall functions are used for the k epsilon model, and k omega model is basically suited for the that is for the low RE formulation when the y plus is less than 1. So it is near the walls. So k omega model is best suited for in that cases. And also there are various advantages and disadvantages of these two models, which you can see on your own. Okay, these are the boundary conditions. So you can for the turbulent case. So this is turbulent. So basically explaining what is Ran's model. So Ran's means Reynolds average Navier-Stokes equation. So we average the Navier-Stokes equation, which gives the fluctuating terms as well. That is the Reynolds stress terms, and the Reynolds stress terms need to be represented as the in terms of the average terms. So in order to represent that Reynolds stress terms in terms of the average terms, we use the help of the eddy viscosity models. So this is a class of turbulence modeling. And under the eddy viscosity models also, there are k epsilon model, k omega model, and k omega SST model, which have their own advantages. So for so if you want to simulate a flow that is highly turbulent, and the separation effect is not present, or the adverse pressure gradient is not present, then you can go on with the k epsilon model. But if there is a high adverse pressure gradient, or the separation phenomenon is very prominent, then we can then k omega model is best suited near the wall regions. And the k omega SST model is the blend of these two models. So it uses k omega model near the walls, and away from the walls when the flow is more turbulent, it will use the k epsilon model using the blending functions. So yeah, that's basic of the Reynolds average Navier-Stokes equations. Okay, for the these are the input parameters for our turbulent flow. So this we are using k epsilon model, and we are we are simulating for the Reynolds number of 2 into 10 to the power 6, and which gives us average velocity of 20 meter per second and kinematic viscosity of 1e minus 5. So and we are using y plus of 200. So this is a very large value of y plus and lies in the log region. Since we are using the y plus of 200, so we need to also ensure that our first cell height lies in that y plus region. So to ensure that our first cell height lies in the y plus region, we need to calculate what our first cell height should be. So the calculation of the first cell height is provided in that reference document. So you can go and see that. And after that, it has also showed how to calculate this expansion ratio. So near the walls, the mesh should be very fine, and then cursor towards the center, because we want to resolve the that the wall effect, that is the that it may be the separation point or reverse pressure gradient is prominent at the walls. So we want to resolve that very correctly. So this is important. So after this, then let's see the post processing part. So if you type paraform built in, then this will launch the paraform. Okay. This is our case for the turbulent case. Now we can also uh, import the same. We can also import our laminar case in the same paraform. So let us see. Let us import both these cases. Okay, so these are the two cases, that is for the for turbulent as well as and the laminar case. So if you want to plot a velocity along the along a cross section in this channel, so if you can see what will be the difference observed between the laminar flow and the turbulent flow of the our boundary layer. So you can untick and select only which is required. So let's just see the ux, that velocity in the x direction. Okay, so this is a turbulent case. Now let us plot for the laminar case also. So you can see that the velocity profile for the laminar case is velocity profile for the turbulent flow is more flattened. So as we have also studied that the turbulence boundary layer will be more flattened than laminar boundary layer. So you can observe also from these simulations. So these are the quantitative analysis that we can do from this type of simulations. So if you also you can also see what how different turbulent model will behave. Like I have only run for the k epsilon case, so you can also run for the k omega case and compare between these models. So yeah, you can also see, apart from the velocity, you can also plot like the different other parameters like the epsilon. So you can see the epsilon is the highest at near the walls, because that in that region still there is a laminar viscosity that is due to the viscous sublayer, and in that in those areas the dissipation of the turbulent kinetic energy will take place. So basically the ADs will be converted into heat energy. So we can see that there is a high dissipation near the walls. Also we can plot for the K, that is the turbulent kinetic energy. Turbulent kinetic energy is also minimum and increases. So only in the at the walls it is quite minimum than at near the walls. So the minimum is caused due to the dissipation of the kinetic energy. So yeah, in this way you can plot different values. So nu t is the eddy viscosity. So eddy viscosity, because the flow will be turbulent more at the center. So you can see that toward the center there is the value is higher than at the walls, because at the walls there is no presence of eddy viscosity, because it is the place where laminar viscosity will be dominating. So yeah, in this way you can compare between the different types of turbulent models, that laminar model, QFCL model, or QMG model as well. So this is for these two turbulence modeling. So as I've already said, that due to time limitation, we cannot go detailedly onto all these values and all these parameters. So you can please refer to this document. This is a very good reference for you all.